Hey everyone, and welcome to This Explainer. Today, we're embarking on a pretty massive journey to decode the actual DNA of human communication. We're going to trace this epic evolution from physical, static-filled analog waves to the absolutely flawless digital architecture of the modern internet. We'll map out the history of signals, the birth of networks, and dive into the hidden logic that literally makes your connected world possible. Let's get into it.
So right off the bat, how exactly did we conquer the immense hurdles of time, distance, and interference? Just think about it for a second. How did humanity upgrade from shouting across a muddy field or sending analog smoke signals to networking the entire globe into a single digital brain? It's kind of wild when you step back and look at it.
Well, the foundation of this whole journey really comes down to contrasting our two primary methods of transmitting information: analog versus digital. Analog systems, like early radio broadcasts or vintage vinyl records, rely on these continuous waves that mirror the natural world. Digital systems, on the other hand, don't flow smoothly at all. They operate using absolute, discrete, and incredibly reliable binary pulses.
To put that into perspective, imagine an analog signal as a smoothly varying continuous ramp. A digital signal, though, approximates that exact same curve by building a stairway out of discrete steps. This technique is known as quantization. By taking a continuous physical sweep and transforming it into a strict set of base 2 binary pulses, just zeros and ones, engineers realized they could recreate signals with pristine clarity. It was a real game changer because it meant leaving the noisy static of analog radio behind forever.
Now, the theoretical genius behind this whole digital revolution was a mathematician named Claude Shannon. See, before Shannon, engineers treated a telephone and a radio as completely different beasts. But Shannon hit the nail on the head and proved a mind-bending concept. It literally doesn't matter if you're using a copper wire, an optical fiber, or a parabolic dish in space. Every single communication system on Earth shares the exact same fundamental building blocks. Breaking those blocks down, every message starts with a source, gets encoded by a transmitter, travels through a channel, and is finally decoded by a receiver. But there is always a villain lurking in step 3, and that's noise. Whether it's a massive solar flare or just a magnetic surge in a wire, noise is completely inescapable. And that is exactly why engineers shifted over to discrete digital pulses. It was pretty much the only foolproof way to guarantee your data survived over vast distances.
Okay, moving on to our next section, speaking in binary logic.
To really grasp how our computers process these digital signals, we have to zoom way into their microscopic brain cells, which run entirely on Boolean algebra. I know, it sounds a bit intimidating, but honestly, it's just a deductive mathematical system built purely around two states, 0 and 1, false and true. By using basic logical operations like and, or, and not, a computer can systematically crunch binary arithmetic to perform incredibly complex tasks.
The real magic here is a total predictability of it all. Specific combinations of true and false inputs create absolute, undeniable logical outputs. For instance, an AND gate only fires a 1 if both inputs are true, while an OR gate fires if either input is true. It's so beautifully simple. But by chaining literally millions of these microscopic logical gates together in hardware, humanity was able to create the modern microprocessor.
Which brings us nicely to our next section, keeping the signals secret.
Because, let's face it, once you turn private human speech or sensitive banking data into easily transmittable binary pulses, you run into a massive new problem. Anyone can listen in. This kicked off a massive arms race in cryptography. We leaped from those early, clunky mechanical rotor machines, like the infamous Enigma from World War II, straight into the digital realm. As our server architecture and computers grew exponentially more powerful, we had to shift to insanely complex mathematical algorithms, like the Advanced Encryption Standard, or AES, which is what secures your bulk data today.
But the true, undeniable revolution arrived in the 1970s with asymmetric encryption. Before this, both parties needed the exact same secret key to talk, which is obviously super risky to share over an open line. Asymmetric encryption completely flipped the script. It uses a public key that anyone can use to lock a message, but a separate, mathematically linked private key to unlock it. This breakthrough is the exact reason you can securely send your credit card info to an online store today without having to secretly prearrange a password with them.
All right, let's look at the next piece of the puzzle, forging the first networks.
So once you figure out how to digitize, process, and securely encrypt information, the very next logical step is connecting all these machines together. Enter ARPANET.
that legendary DARPA project from the late 1960s. They had dozens of totally incompatible computers and managed to solve the connection problem with an ingenious concept called packet switching. Instead of sending a file as one massive, fragile stream, the data gets chopped up into smaller, discrete chunks, or packets. This ingenious move prevented network traffic jams and ensured your data survived, even if massive parts of the physical network suddenly went dark.
To actually picture how these packets travel over a wire, it helps to imagine a series of nested envelopes. Your raw application data gets placed inside a TCP or UDP header envelope. Then, that envelope gets stuffed inside an Internet Protocol or IP wrapper. And finally, the whole thing is framed by an Ethernet layer so it can ride the physical wire. As your packet jumps from router to router across the globe, these envelopes are constantly being read, stripped away, and replaced until the core message safely reaches its destination.
Next up, protocols powering the internet.
To govern this insanely complex web of digital envelopes, network engineers had to develop a strict hierarchy of rules. They crowdsourced these globally through the request for comments process, and the two main transport rules they landed on are TCP and UDP. TCP acts a lot like certified mail. It meticulously tracks every single packet and demands a resend if even one drops. That makes it absolutely perfect for downloading a file where you need every byte. UDP, on the other hand, is more like a reckless postcard delivery. It just shoots packets out as fast as possible with zero guarantees. And honestly, that's exactly what you want for a live video call, where speed matters way more than absolute perfection.
We actually see very similar structural differences higher up at the application layer too. Take FTP, for instance, the File Transfer Protocol. It's this heavy, robust method that actually establishes two entirely separate connections, one just to send the commands, and another dynamically assigned connection just to transfer the actual data. When you compare that heavy-duty server setup against the much simpler lightning-fast UDP mechanism, which just relies on a single datagram transmission, you really see how different tools are built for different jobs on the network.
And finally, our last section, the World Wide Web.
Think about everything we've covered so far. We took analog waves, turned them into digital bits, mapped out Boolean logic gates, secured everything with cryptographic keys, and tied it all together with packet switching protocols. All of this, underlying invisible architecture, completely paved the way for the World Wide Web. It's a fascinating direct lineage. The military's ARPANET published its very first rules in 1969. By 1974, we officially coined the term Internet. And then, in 1989, a scientist at CERN named Tim Berners-Lee wrote a civilian proposal that quite literally changed the world forever. But here's the thing. Berners-Lee's absolute stroke of genius wasn't inventing some brand new physical network from scratch. No, his genius was merging the existing data networks with hypertext documents and personal computers by creating HTML to format pages, HTTP to transfer them, and URLs to address them. He built this incredibly powerful, easy-to-use information system, and it just sits perfectly right on top of all the complex server architecture and internet protocols we've unpacked today. So just take a second to consider how incredibly far we've come. We started with analog signals and sine waves, learned to quantize them into binary logic, secured them with advanced cryptography, and eventually built a globally connected digital web. We've essentially mastered the physical limits of our planet to communicate instantly. So, as we stand right now on the brink of an era defined by things like quantum computing and artificial intelligence, what massive communication revolution do you think lies just over the horizon? Thanks so much for exploring this with us. See you next time.